SwayamPrabha. Digital India. Educated India.
Hello and welcome to this course, ME762, the last lecture today on VAL programming. In the last class, we started studying the basic words that are used in VAL programming, and we said the structure of the program is similar to that of the basic program. And we looked at the variables, variable names to define points, then motion control commands, move, moves, then we looked at hand control, open, close, and then logical statements. So today we'll be looking at how to have communication between machines because the robot has to interface with other machines. Could be a conveyor, could be another machine, could be an AGV, and there has to be communication between the machines. So we'll look at that. Then we'll look at basically how signaling is done in terms of how a robot communicates with another machine using channel lines. Then things like ADCs, DACs, and then finally we'll look at an industrial robot program and look at the way actual programming is done in industries for industrial applications. So today we are looking at robot programming in VAL 2. In the last class we had looked at the basic structure of a program, and we said that the program consists of these four parts. First is constants, variables, data objects. Constants, variables, as the name indicates, are constants. Then variables are variables which can take different values, and then data objects. The second thing we looked at was motion control commands. That is, when the arm moves from point to point in space, what are the motion commands? The third is robot hand control, which is essentially the robot has a gripper. So to do a particular task, it has to catch an object, maybe place it somewhere. So robot hand control. And then the last is robot program control and input-output control. Program control is essentially for logical statements to take the to go in between the programs from one point of the program to the other point. For example, if you have a subprogram and a subroutine, or from one line you want to jump to another line, depending on some logical condition, then we have a program control commands. And then input-output control, this is more for interaction with other machines. So let's revise very quickly what we talked about in the last class. So the first thing we said in the last class is that the variables can have a name and they can contain a letter like P1. So this variable P1 essentially indicates a point, and how a point is indicated in space is by giving the three position coordinates of that point, x, y, and z, and then the three angles of the end effector at that point. So if I have a robot here and we have the end effector which is at this point, okay, so this will be my x, y, z, and the other three are going to be my roll pitch yaw angles. Okay, so three of this and theta, alpha, and gamma, which are the roll pitch yaw. Now, if I don't put the theta, alpha, and gamma, I just say x, y, z, then it will have a default. If this one is equal to 0, then there is a default also. Okay, default setting is already there. So depending on whether you want the end effector orientation also, for example, when you're picking an object, their orientation of the end effector is very important. Whereas if you're just moving in space from one point to another point, then orientation may not be important. So this is how we define points in space, and a robot essentially moves from point to point. So point 1, point 2, point 3, that is how we define points, and a robot essentially goes from point to point. Now move and moves. So the robot hand has to move from one point to another point. So the very simple command is move and moves. And we saw in the last class that if you want to go from one point, suppose we are at the point P1 here, and you want to go to another point P2 there. Okay, so if you say move P2, okay, what is the trajectory that the robot is going to take? This is an interesting question, because even for human beings, when we move our arm from one point to another point, what is the trajectory that we take? Because our hand has 7 degrees of freedom. This one here has 3 degrees of freedom. So it can have very large number of trajectories, infinite trajectories. Okay, so it can go like this, it can go like this, it can also go like this. Okay, it can go in a straight line. So which trajectory will it take? So the trajectory is basically decided by the controller okay, depending on the least angle norm. So this is basically called the least angle norm, and this basically means that move the least number of joints to minimize energy. For human beings also we do the same. So when you move from one point to another point, when you move your arm from one point to another point, you're going to move the least number of least angles. Okay, that will ensure that our energy is consumed. Now it does not move in a straight line, essentially because moving in a straight line means finding infinite points on the line, doing inverse kinematics for each point, and then going to that point, which takes a lot of time, is computationally intensive, and it consumes more energy, okay, and is very, very slow. So what is basically done is we use least energy norm. Now in cases where you have to move in a straight line, there we use S. So example is assembly. Okay, so in assembly operations, basically we have to move in straight lines. Okay, pick place operation is another one. Pick place application is another one where you have to move in straight lines, and there we have to use moves. Okay, this means move in a straight line. Then draw, we have seen, is an incremental command, which means that if you're making a correction, then we are going to use draw. Approach is for picking up an object. It approaches the point P1 and keeps a distance of 50 along the z-axis. This we saw in the last class. Depart is after catching, it goes up along the z-axis to the point P1 and keeps a distance of 50. Okay, approach S and depart S, they basically mean the same as approach or depart. Now the hand control command, open and close, that is essentially, these are open loop commands. This is open loop commands, and they are faster. Okay, whereas this one is a closed loop command. Okay, this is a closed loop command, and this is slower. Now in terms of execution of the program, we have seen that the compiler will execute this in closed loop. That means it will execute this line. Say for example there is 20 open I, then it will execute this line. After it is completed, then only it will go to the next line, otherwise it won't go. Whereas in open, it will simply execute the line. Execute the line means it will tell the gripper controller, which is probably it will just inform the gripper controller that open. Now the gripper controller will take its own time to open because it's pneumatic. Okay, so it will take some time to open. So in that time, it will go to the next line. So this is an open loop command, this is a closed loop command. So when we are catching an object and we are lifting an object, then we should be careful of using open eye and close eye. Otherwise, there is a chance of an accident. Now speed, IPS, speed of the robot is the maximum speed. So it can be in inches per second or it can be meters per second, and we can have trajectories which are made up of different points. For example, A1, A2, A3. So A1, A2 and A3 are 3 different points. Okay, pause time gives how much delay should be there. Okay, so delay 1000 means delay by 1000 milliseconds. So this is in milliseconds. Now we also saw that a robot has to interface with other machinery. Okay, otherwise it can't work. So basically this is a conveyor on which parts are coming, and when a part comes, the conveyor should know that the part has come. So for example, I put a sensor here, okay, inductive sensor or proximity sensor, which we have studied, and connect it to the robot through a channel. Let's call this channel 1. Okay, now as soon as the part comes, the conveyor should stop, and the conveyor should stop and it should inform the robot that the part has come. Now the robot should go and pick it up. Okay, now after picking it up, the robot should again inform the conveyor that I have picked up the part, please start now. Okay, so the first thing is the part has arrived. Part arrived. Okay, the second is picked up. Okay, so this information has to keep going from the conveyor to the robot and from the robot to the conveyor. Now today we'll see how do machines communicate at the lowest level. Now the communication can be with other machines. There are so many machines now. There are machine 1, 2 and 3. There is a conveyor here. There can be an AGV which is bringing parts. Okay, so say a mobile robot, which is an unmanned guided vehicle, automated guided vehicle, which is bringing the parts. Okay, so all of this will require communication. So how do machines communicate? That is something which we'll be looking at today. Now at the lowest level, the communication is with simple on-off kind of sensors. So if you look at this example here, the communication requirement is actually very simple. For example, it is like on-off kind of communication. What do I mean by on-off? It is it is yes or no kind of communication, yes or no kind of communication. Okay, so yes will mean 1, no will mean 0. So a part has come means 1, so it will communicate and say 1. If part has not come, it is no, so it is 0. Okay, whereas after the robot has picked up, it can simply tell the conveyor that yes, I have picked up, which is 1, and no, I have not picked up is 0. So essentially it is 0 or 1, which means on or off kind of communication. Okay, so at the simplest level, this on-off communication is enough to get the simple jobs done. But if you need more complicated kind of information going through, for example, if you're having a robot which is assembling, so this is a robot which is assembling this part. Okay, so we have this part and the robot is assembling it. Now, so the robot is holding this part with a gripper. Okay, so this is a robot gripper and is forcing this part in. So we have to measure forces and torques somewhere. So maybe at this point we have to measure the forces and torques which are acting, because if there is too much force, it will damage the part or damage the robot. So for interaction of this nature, where there is forces sensors, torque sensors, there could be other sensors like vision could be there. Okay, in those, ultrasonic sensors could be there, checking distance from somewhere. Okay, so for those applications, you may not be, it is not on-off kind. Okay, this is a continuous kind of, so you're measuring the force and the force measurement is continuous. It is not on-off kind. Okay, so in that case, we may require more advanced sensing kind of capabilities and more advanced communication. So we'll go on slowly as we go along, we'll see how this is done. So the simplest communication is by on-off kind of communication. On means yes and off means no. This can also mean 1 and this can mean 0. In terms of the machine language, it basically means 5 volts and 0 volts. Okay. So we said that the robot is connected by, the robot and the conveyor are connected by wires. Okay, so this is my conveyor where the part is coming and this is my robot. And we said that the robot and the conveyor are connected by what we call, it is connected by channels. So a channel is essentially a wire which can carry a voltage. Okay, so this is channel 1 and this is my channel 2. Okay, so when the part has come, the part will be sensed by a sensor and the conveyor can tell the robot, make this channel high. So it will make this channel 5 volts. Okay, so the conveyor is telling the robot that the part has come. So how will it do that? It will simply make this channel high. That means it will pass 5 volts. Till now it was 0. That means the part is not there. Now the moment the part comes, it will make this channel high. Now the robot receives that and it understands that this channel has become high. So the part has come. Now after it picks up, it has to tell the conveyor that I have picked up, now you proceed. Okay, because after the part comes, the conveyor stops. The robot normally picks up after there is a stop. Okay, after the conveyor stops. So what the robot will do now after picking up is now it will make channel number 2 high. So it will make this high. Okay, so simply by making channels high and low, which is corresponding to yes and no, 1 or zeros, okay, the robot can understand and the conveyor can convey and the robot can also understand what is going on. So at the simplest level, we have on and off kind of communication. Okay, on is plus and this one is minus. Because it is 5 volts, we need not write 5 volts, just plus minus will indicate what it is. Okay, okay, so now let us look at this kind of communication. So let us look at the kind of signaling or the syntax for the signal, for the signals. So this is the syntax. It says signal 2, 3. Now signal, you mean you understand what is the meaning of signal, so it makes it high or low. So this is high, low signal. This is the channel number. So this is channel number, and plus and minus is high and low. Plus minus equals to high or low. Okay. Now if you don't write anything, then it is plus. If it is minus, then it is low. Okay. So look at this statement, signal 2, 3 basically means channel number 2 is high and channel number 3 is low. Okay, so in terms of voltage, this is 5 volts and that is 0 volts. Okay, now let us go again. So we looked at the syntax. Now let us go on top here and look at the logical statements. Now these are logical statements that are there for the robot to perform logical operations. For example, go to 20. So it basically means go to line number 20 given here. Then go sub return. Now in this robot programming, A robot would be doing repetitive tasks. For example, it is going to pick up an object from somewhere and then do some indexing and keep it in some index position. Okay, so one bad way of writing a program is that you can repeat the number of lines over and over again. For example, move 1, then open, then moves P2, and then close, then depart. So you do that. If you have to pick up 1,000 times, you write that 1,000 times. That's a very bad way of writing a program. Now, a good way of writing a program would be if you can write a subprogram for repetitive tasks. So whenever it has to pick, it can go to that subprogram and pick. Or if it has to index, it can go to the subprogram and index. Okay, so what I mean is, this is my indexing. So this is the palette, for example, where it is keeping. Okay, so it has to keep in all of these places like that. So basically what we are saying is it will come here. It's a coordinate, right? It's a position coordinate. And these coordinates are fixed in this direction or this direction. So all it needs to do is, if I define this point, let's call it P1, then next time I just increment P1 by the distance here, which is, let's say, del x. And it moves to the next one, next one, next one, like that. Okay. So basically indexing is one case where we can do by using a Go sub program, or this is a subprogram or a subroutine for indexing. So this point pick P1, we define only once. And then every time it goes to the subroutine, indexes that P, depending on where it is going to keep. And then it comes back. So there is a go sub and a return statement. So we have a go sub with the name of the subprogram and a return at the end to come back to the main program. Okay. So this is very commonly done for indexing. Okay. Then pick and place. Then for spot welding, where you have to go to different positions. Then the other statement is if then else. This is a logical statement. So if some condition is true, then do this, else do something else. So that is your if then else. Third is pause and proceed. Okay, pause we have seen is delay, and proceed we know is continue. So if then else is some condition here. So if this condition is true, then do this. If the condition is false, else do something else. Okay. So using this program control statements along with this signal syntax, we can make meaningful lines. Okay. So for example here, if signal 2 plus minus 3, then do something. Okay, so in this one, if you see, this is saying if signal on line number 2 is plus and line number 3 is minus, then do something. Else, you can say else, wait. Okay, else pause. Okay, say pause 1000. Okay, so it will check this signal, else it will pause 1000. Okay, so if signal this, then move P1, else pause 1000 and check the signal again. Okay, then wait signal. So this is wait signal. So it will come here and wait until the signal on channel number 1 is minus and channel number 2 is plus. So this is wait sig. Okay, so signal short form is sig. This channel number plus minus. Reset turns off all external signals. So the robot can receive signals and it also can give signals, send signals. Okay, so receiving and sending signals the robot can do. So at the starting of the robot should turn off all external signals. Okay, and set them to 0. And this is what it is doing just at the time of start. So reset sets off all external signals to 0. On 2, off 3. These are individual signal lines. For example, on 2 would mean make channel number 2 on. Okay, so for example, after picking up, in the example we saw some time back, after the robot has picked up the part, it has to inform the conveyor that I have picked up. So on channel number 2, it will make it on. It will simply say on 2. So now the conveyor understands the channel number 2 has become on. So it should start the conveyor again. Off 3, for example, it will make it low. So this also would mean something logically. So these are program control commands, and these are the communication commands. This is for communication, and those are for very simple program control commands. Now we have seen that all signals are not on-off type. Okay, high-low kind of type. Now, depending on what sensors they are using, you'll be getting the signal whether it is going to be analog or it will be digital. Now there could be counters. So analog signal is something like voltage. Okay, so a force signal will be an analog signal. So you'll get a continuous signal. So analog basically means continuous signal. For example, we have a continuous signal like this. Okay, so some signal is just coming like that. So this is my time, and this maybe is force. Okay, so this is a continuous signal, and it's an analog signal. We can have a digital signal where this is digitized. So it basically means I'm going to split this at, I'm going to sample this at particular time instance, and basically what I'm going to get is signals like this. Okay, so this is my T and this is my F now. So this is an analog signal and this is a digital signal corresponding to the same signal, but one is analog, the other is digital. Okay, now electronic equipment like computers, controllers can understand digital signals. They cannot understand analog signals. So there has to be some converter from digital to analog signals. Okay, and those are called ADCs, analog to digital converters. Now you may also have to go in the reverse direction, which is your digital to analog converter. Now, so on the real world, on the left hand side, so this is the world, the real world I mean, and there are different sensors which are being used. Okay, there is analog sensor, digital sensors, there will be counters. For example, the robot will do some task very large number of times. For that, it has to count and keep track. So there is a counter. Then there are other kinds of sensors for temperature, force, pressure. Okay, these are analog again. Now, in between the robot controller and the sensor, there is a piece of hardware which is called the data acquisition hardware. The data acquisition hardware is the one that converts the signal. Okay, from if an analog signal is coming, it will make it digital and then give it to the robot. Otherwise, the robot will not be able to understand. Now, so data acquisition is basically a phenomenon in which the real world can be translated and manipulated by a computer-based readable signals, which basically means converting it to digital form normally. Now, analog signals, as we understood it, as I just explained, analog signal is a continuous signal that can be at any value with respect to time. Some examples are voltage, temperature, pressure, sound, load. These are all analog signals. Okay, and analog signals basically have these three things that characterize them. One is the level of the signal, one is the shape of the signal, and there is the frequency of the signal. Okay, primary characteristics of an analog signal. And what you can see is that they are continuous. Now, digital signals are analog signals which are sampled at a particular frequency, resulting in a digital signal. Okay, and digital signal values have values only at certain instance of time when they are being sampled. So in between, it doesn't have value. Okay, or it has the same value as the previous sample. Now, electronic equipment like computers, controllers, they can understand only digital signals. They don't understand analog signals. So the sensor information has to be converted. Okay, so this is an example of a digital signal now. Okay, so on-off state, our on-off which we are talking about is on or off, two states only. Okay, whereas the other ones can have a lot of digital signals which have a particular frequency and they have a particular amplitude also. Okay, so this is a digital signal example. Now, to convert an analog signal to a digital signal, we use an analog to digital converter. So this is called an ADC. Okay. So analog, this ADC basically converts analog to digital signals, and the signals can be temperature, force, okay, or any other kind of torque, okay, distance. Now, DSC is the reverse of an ADC. So this is a digital to analog converter, and digital voltage converts to analog voltage. Now, robots use ADC to convert forces, distance, etc. from analog to digital value and to understand it and take some decision. Okay. So as we go along, we will see how the robot uses this. Now, the syntax is IO put and IO get is 1. Okay. IO put means you are putting a particular voltage onto a particular channel. IO get means you are getting the voltage from that channel. Okay. So we can say I get this one. Is basically from channel number 1. We can put a variable, say V1 is equal to IO get channel number 2. Okay, so this variable V1 has been assigned whatever voltage is coming from here. Okay, it will be digitized and it will be assigned to this variable. Now, the syntax for using ADCs and DSCs are DAC1. Now, an ADC will have a number of channels. Okay, so could be 6 channels. Now, a DSC also would have a number of channels, which could be up to 6 channels, could be more. So, which channel are you referring to? So, they are numbered like this 1, 2, 3, 4, 5, and 6. So if I'm referring to channel number 1 of the ADC, then I say ADC1 is equal to sensor 1. That means the ADC channel 1 has been assigned to sensor 1, and whatever value is coming at sensor 1 is going to get converted on ADC channel number 1. And then we can assign it somewhere like this: variable 1 is equal to ADC1. Okay. So we understand that ADC channel number 1 is measuring whatever the sensor that has been put there. For example, let's put a pressure sensor there. Okay, just for example, the sensor 1 is a pressure sensor, and the pressure sensor is getting an analog value, is converting that to digital, and then is giving it to variable 1, which is the variable, and then it is going to take some action based on that. For example, if this is pressure, or let's take the example if it's force. Okay, this is just an example. So suppose we go back to our earlier problem of assembly, where this part is being forced inside here, and there is a force torque sensor. So the robot wrist has a FT sensor, force torque sensor here. So it can measure the force, 3 forces, 3 moments acting there. So we can say that ADC1 is sensor 1, and if variable 1 greater than say 10 newtons, then stop. Okay, or then end. Okay, else proceed. Okay, this is just an example, so line number 10. So if variable 1, which is connected to ADC1 here, okay, is greater than 10, so for example, if the force being applied in this direction is more than 10 newtons, okay, then end the program or stop, else proceed, continue going down. So the logic here could be that we are doing the assembly, and we are monitoring the force torque sensors at the wrist. So as the part is being forced into the cavity, so we are monitoring the force, and if the force is exceeding 10 newtons, okay, then it will end the program, else it will proceed and continue moving it down. So when it hits this, what will happen is it understands that it has hit this part and the force is exceeding 10 newton now, so it will immediately end the program. Okay, end the program or end that process and do something else, or it will keep proceeding in that order. Okay, now going back here, so these are the various signals: ADC, DSC. Then ADC1 is a constant. For example, ADC1 is DSC channel is equal to 3 plus constant. So whatever is there on DSC channel number 1, it will make it the constant value plus 3. Okay, so this is normally an output to another machine. So it is making a digital signal and giving it out from channel number 1. In the previous case, it was converting the analog signal on channel number 1, making it digital, and then giving it to the robot controller. So this is a very standard command that is used when we are taking input from various sensors, and we can use it like this, as I just explained, for a case of assembly of 2 parts. Now other computations that are done. So the other computations that are done are like sine, cos. So we can give these terms and it can compute by itself. Square root, SQRT is square root of A, EQ is equal, NE is not equal, GT is greater than. So I had just used greater than here. Okay, so if in line number 10, if variable 1 is greater than 10, then end, else proceed. So this greater than is a comparative statement, and we are saying that it is GT. NE is not equal, EQ is equal, less than is LT. Okay, less than. Okay, so these can all be used for logical operations. Okay, so this can all be used for various kinds of. Now, we saw that the robot is programmed either by using a teach pendant. So in a teach pendant, we manually take the teach pendant and manually toggle the keys and take the robot to some position in space to do some task. Now, why do you need a teach pendant? And why can't you always use a robot program? Now, the answer is very interesting in the sense that if you have a robot like this, the robot is here, and suppose you are keeping an object on a table, and I want to go and catch this object, that my robot is here. Okay, that's my robot, I want to go and catch. Now, it must know what is the coordinate of that point. Okay, Now the base of the robot is 0, 0, 0, we know, but I need to know the coordinate of that point. Now the coordinate of the point has three parameters, x, y, z, and theta, alpha, gamma. So there are 6 parameters. Now no sensor will actually give you the 6 parameters of an object in space. So if I say with respect to this base 0, 0, 0, what is the x, y, z, theta, alpha, gamma of the object here? How would you find it? There is no way. Okay. At most you can get the distance by using a laser like this, but that doesn't give you the orientation. Okay. So we can use things like computer vision, but then again there are other issues. Okay. So please note this point, that when we have to find the coordinate of a point in space, position and orientation, it's not very easy. So one way could be that using the teach pendant, you take the robot and place the gripper like this, and then look at what is the position orientation of the end effector with respect to the base. So when you're using the teach pendant, in the memory and the display of the teach pendant, what is the position orientation appears, okay, automatically. So you can now know that, okay, this is the position orientation of this part with reference to the base now. And then after that, you note this part, you note any other required part, then you can write a program which is using VAL2 the way we have seen it in this class. So teach pendant is used for teaching and mainly for finding coordinates of points in space, because it is very difficult to find the 6 parameters of a point in space. The second is program-based control. So the desired task is written as a sequence of motions in a language such as VAL. These motions can then be played back. Okay, so we have just looked at VAL programming, how to write a VAL language. We'll see that in more detail. Now something to note here is that robot programming is actually extremely complicated. Why? Because a robot will not be working alone. A robot will be working with many other robots. They'll be working with other machinery, and they'll be working in complicated workspaces. So you can look at this example of an industrial robot spot welding vehicle bodies. Now, if you go to any industry, automobile industry, you'll find that the robots are doing spot welding. And how many spot welds per car? Very high number, 2,000 to 3,000. Now, how many robots? Large number of robots, sometimes 3 robots, sometimes 6 robots. So not only must the robot go into very complex spaces, for example, it will go inside from here, it will go inside there and do welding. And it has to do it very quickly and not hit anything else. It must not also interfere with the motion of the other robots, right? Because if it starts interfering with the motion of the other robots, it will become dangerous. It can hit something, there can be an accident. And getting coordinates, finding the trajectories into complex spaces is a challenge in itself. Okay, so it is extremely difficult to manually do programming of this kind. So although VAL language program is very easy, and it appears that we can very easily write a program and make the robot do something, but in reality it is extremely difficult to write a VAL language program for an industrial application like this. So how is it done? So the first thing that is done is it is done in simulation. So the robots and the car body, for in this case, are simulated. Okay, so there is a simulation in which you have the car body, you have the various robots doing the particular task. Now in the simulation is also optimized. So optimized for motion planning. Okay, that means these robots can do the task in infinite ways. Which way are you going to do such that your time is optimal? Optimal in terms of least time. So that is something that is done in terms of the motion planning. Now the motion planning also takes care of interference, that there is no interference between the robots, and there is safe, means there is no interference, plus it doesn't hit something, and it is optimal. So you can understand that this is a very challenging and complex problem. Simply trying to take the robot inside the car body, do in different places simultaneously with other robots, okay, is an extremely complex problem in motion planning. So first it is done in a simulation, then number 2, it comes to the real world. Okay, after it comes to the real world, it is checked on a dummy kind of an. So we will not put a real car; it will be put out of wood or plastic. Okay, so this car will be made with wood or plastic, and then the robots will be operated and seen whether it is hitting something, or because it is wood or plastic, there is a chance that even if there is an accident, it will not be major. Okay, now why do you need to do that? Now we need to do that because we noticed, or what we studied in the last class, is this 3 terms called accuracy, repeatability, and specifications. Control resolution, accuracy, and repeatability. So in a simulation, once you come to the real world, the real errors will start coming now. Okay, the errors in terms of mechanical errors, in terms of your temperature variation, in terms of sensor noise. Now those errors are going to be added on to your simulation now. So even if the simulation is perfect, in the real world you can find that there are errors now. And there are going to be errors. So you have to consider those errors now in the real world and make changes if required. Then it goes to the real part, real application. Okay. So we see that this is a very complex procedure, and there are companies which specialize in this kind of applications for robots. And so if you go to any assembly line, for example, if you go to Tata Motors in India, you'll see that the robots programs which are running, a lot of the program are simply running, and the language is also not English. It could be in Japanese, because the original manufacturer of the robot could have been Japanese. So very often the full assembly line programming is done by a company, and the people who are running the assembly line don't change that program. They cannot. Okay, they don't know how to change the program also. And the actual cost of applying a robot actually is coming from here. So the simulation cost, real world application cost, then updating the environment, updating the software, making changes, that is what adds to the cost of using a robot. And the total cost in an assembly line, the soft cost, is sometimes as high as 70% of the software guarantees, AMCs, things like that. Okay, so although it is easy to write a VAL program, to use a teach pendant and try and program, but it is not possible for one person to write a program for this kind of industrial applications, and there are specialized companies which do that. Now the second kind of application that are important is lead through teaching. Now there are tasks which require human experience. Okay, human experience is required. For example, arc welding is one. Okay, so arc welding is an application where you're joining, say this is a weld. Okay, so this is making a V weld in two parts, and there's a consumable electrode which is there, which is held by the robot. Okay, and this is the arc, the arc which is melting the consumable electrode and is depositing the weld here. This is an arc welding process. Now, if you look at the arc welding process, how it proceeds is that the human operator will take the electrode, touch the part and short it, and then lift the electrode. So if he first touches, then he lifts it and creates the arc. That's how the arc is created. And then he moves the electrode in a particular sequence. Now, as he is moving, the electrode is getting consumed. So there are two motions here. If I take the top view of this and draw it here, so this is my top view, this is my V weld from the top view. So he is depositing the weld and he's also moving like this. Okay, and plus he's moving the electrode down. So there are two motions here. One is this bead formation or weaving, plus the electrode has to come down. Now it is very difficult to mathematically explain or mathematically write this beading in terms of an equation, or how much of this should be coming down with respect to time in terms of an equation. So if you can't write it in form of an equation, okay, or that means you cannot define the points. It is basically points. So it was here, it has to come down, means it has to come here. So you have to define those points. Now how do you define if you can't write those equations? So this is where human experience comes into picture. That a human being knows, an expert welder knows how to weld, what is the arc, how he should put the electrode down, what is the rate, what is the beading pattern that is going to be done. So an expert welder knows this, whereas to transfer this to a robot in terms of an equation or points is extremely difficult. So what is done is this lead through teaching. On one side we have the human welder. He has a joystick which is exactly like the electrode gun, and he performs exactly the same motion that he was going to perform when he's doing the weld. And at every instant of time, the positions and the orientations of this gun is recorded in the computer. And then it is transferred to the robot side, and then it is played back. Now the robot does exactly the same thing. So this is how lead through teaching is done, where a robot learns from a human expert welder. So this is another example where a human is very good at doing a job and he can teach a robot to do the task. Now let's look at a sample program. Now this is a Puma robot, 6 degrees of freedom. We had studied about Puma forward kinematics, inverse kinematics in the earlier classes. Now what is this task? This task is to pick up objects from a pallet, which is shown here, one at a time, and then drop it in this chute, which is shown here. Okay, so pick up a part from here take it like this, take it there and drop it inside. Okay, that is the task that the robot has to do. Now, how many parts are there? There are the top view of this pallet is shown here. So there are 3 rows and 3 columns. So there is 12 parts. Now the dimensions of the pallet is also shown here. Okay. So this is what I talked about indexing, that you have to index. So this information is given. What is the distance from here to here? That is equal to 50. Okay. And from top to bottom, it is 30. Okay. So the distance is given. Now the robot is going to operate in, the robot has to be taught points in space, right? So we are teaching it this corner point first. This is the corner point. So this point is being taught. Now this is a case where we can teach using a teach pendant. Okay. So when the pallet has been kept there, the robot doesn't know with respect to its 0, 0, 0, where is the corner. Okay. So it has to be taught that point. Now it's difficult to get the corner point from a sensor. So one way would be you use the teach pendant, take the robot to there and see what is the position orientation, and then say corner is equal to that. Okay. Next is I can keep shifting this corner point. So it is here. So I first will shift it to the top here, catch this object, pick it up and put it in the queue and come. Then I'll shift my point to the next one. Okay. I know it is 50 mm on the right. So I index the corner point to move from here to here first, then from here to here, then here to here, then here to here. Okay. So what I'm doing is I'm just shifting the corner point by a distance of 50, and it is coming to the top of each of these objects. Okay. Then from here I take it back here. I'll take it here. Then I'll take it here, here, here. Essentially the corner point is being shifted in the X direction or Y direction. Okay. And then I take it here, 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 and here. So this is done by a subprogram. Okay. So we teach it the corner point, and then every time it has to pick up an object, we change the coordinate of the corner depending on how much we have to move it, either 50 or 30, and then we pick it up and go and drop it, right? So this is how indexing can be done for picking up an object. Otherwise, the bad way of doing it would be that you find the coordinates of each of these points. Okay, so I find the coordinates of each of these points. I find this, I find this, I find this, I find this. And I say this P1, this P2, this P3, and every time I say go to P1, go to P2, go to P3, and keep doing that. That's a bad way of writing a program, although it will still work. Now the other advantage of writing a program with an indexing or a subroutine subprogram is that if you change the number of rows and columns, your program will still work. So for example, if you're writing a program for spot welding, okay, every time you have to write a program for spot welding is extremely time consuming. So what we could do is we could write a program which can be modified easily into another program, or somebody else could use it as a subprogram. So somebody who writes a main program can call this subprogram for indexing or for spot welding, and the person can do, the robot can do the spot weld and can go back to the main program. Okay. So nowadays this is the basic modular way of writing programs. So modules. Okay. So modules for indexing. Okay. Then modules for spot welding. Okay, and others. So these are modules. So the main program can call these modules and perform that task and then go back again. Okay. So this is the way the most programs are written these days. They are very modular, and you can keep shifting the programs around. Now let's proceed. What is the logic that we are going to follow here? Now the first thing that we need to do is we need to fix our constants and our variables. So what is the constant here? The constant is the number of rows and the number of columns. We need to define that first. How many rows are there and how many columns are there? Then I need to define my corner point. Okay. So corner is a variable now. It is a variable name which will get shifted each time from here to here to here. Okay. So what is the logic that we are going to follow? Let me explain the logic first. So the logic is, first we'll define the rows and columns. So it is 3 rows and 4 columns. Then what we'll do, we'll define our point of corner. Okay. And then I will shift my corner point from here to the top of that object. Okay. Then I'll go and pick it up, go and drop it in the queue. After we pick it up and drop it in the queue, what I will do is I will index. So this corner point which was here will be shifted to the top of that. It is simply moving it by 50. And before doing that, before shifting by 50, it has to check whether I have exceeded my rows and columns. Because once it has come here, it needs to check, it should not go here. It needs to check if it has exceeded that 4 columns. If it has exceeded 4 columns, it should go from here, it should go here. Okay? So it can go from here, it can go there, or it can go here, it can go here, like this, like whichever way you're indexing. Okay? So in this particular case, from here, it checks that it has exceeded 4 columns, and then it goes there. Goes there means it comes down by 30, okay, and goes backward by minus 150. So that is the way we are going to write the program. The advantage of writing the program like that is that if I change this to say 5 and this I change it to 6, the program will still run. Okay, so the same program is adaptable to different palettes. If different palette numbers are there, if different number of objects are there on the palette, the same program will work, and I simply need to change that. Okay, so that is writing a program intelligently, how it works. So let's start off. First thing that we do is to define, there is a remark statement. Okay, so the program is called dpalette1. There is a remark. Now the VAL program does not execute a remark statement. Okay, so remark is essentially for the programmer to know, or somebody who's reading, what is this program all about. So remark means corner and cute locations are taught. Okay, that means the corner of that palette and the cute locations have to be taught. So the cute location also, because it has to go here and drop from here, so it must know that position. And the corner, of course, because it's starting from there. So the first thing that we define here is we give the constants. So max column and max row. So max column is 4 and max row is 3. Okay, this is defining the number of rows and columns on the palette. Then it sets the row to 1 and sets the column to 1. That means I'm going to start from my column number 1. I'm going to start from here. Okay, so I'm going to start from here now. So that's row 1 and column 1. So first it defines max rows and max column. Then it sets row to be 1 and column to be 1. Then it sets pick. Okay, this word set is similar to assigning a variable name. So pick corner. Okay, so we are assigning the variable name pick to the coordinates of the point corner. Corner is already taught, which is given here. Okay, so I'm calling the pick point, the variable name is pick, and I'm making it equal to the coordinates of the corner, okay, which are already taught from here. Then what I do, I shift pick by 20 minus 20 60. I shift pick by 20 minus 20 60. So I'm here. So I shifted by 20 means this side, minus 20 means down, and 60 is the height of the object. Okay, so the height of the object is not given here. So let us assume that this is going and standing on top of the object. Okay, so it is from the object, it is so from this is 25. So the gripper is going somewhere here. Okay, and this is my 25. Okay, so the 60 is from the 0 of the robot. Okay, from 0 of the robot, it is 60. That's an assumption we are making. This is my object. Now, what we see here, we are shifting the pick by 20 minus 20 60. So I'm going on top of the first object now. So this coordinate is 20. So it has gone to the top of the first object and is sitting on top. It's just on top of the first object. Then we say move I. So please note it is I. Okay, so move, sorry, not move, it is open I. So please note that it is open I, so which means that open immediately. So it will open, it's a closed loop command, it will open the gripper. Then it says move pick. So it has moved to pick. So what was the pick point? The pick point was this point. Okay, sorry, that was not the pick point. This was the pick point. We have defined this as the pick point. So this is my pick point. Right, so that is my pick point. So it has moved to pick point there. Now it has gone on top of the object. Then we say draw 0 0 minus 25. So minus 25 means go down. So it will come to minus 25. Then close I. Okay, it captures the object. It is again close I. Then you draw 0 0 plus 25. So you go up. Then you move to cute. And once you go to the cute, you open I. Drop the palette. Drop the part. And after dropping the part, you go to go sub palette. So this is the go subprogram palette. So this is the subprogram palette. So what it does is, in The subprogram palette, it takes the column. We had started with 1. So column was 1. So it becomes 1 plus 1, which is equal to 2. So what it has done is it has set the column to 2 now. So it will shift the pick from here to here now. Okay, that means just to simply shift by 50. So what it does is it is setting the column to 2 now, and it is also checking that it is not exceeding the maximum column. Okay, so we have 4 columns here. So if it is here, it should not go there. So it is checking that if it is exceeding. Now if it is exceeding, it will shift it there. Okay, so please note this logical. If column is greater than max column, then 20 is here. So from here it comes here. So then it shifts the row. Okay, so what it is doing is, if it has come here, it is checking if the column is exceeding. Yes, it is exceeding. Then it will shift the row and shift it down. Shift it down and shift it there. Okay, so that is the logical statement. So if column is greater than max col, then 20. Now if it is not, then shift pick by 50, 0, 0. So it is simply shifting by 50, 0, 0. So it is shifting from there to there. Okay. Now, so it has gone to the top of the second object. Then it says go to 10. So this is my go to statement. It says go to 10, it goes there. So again the same, move pick, draw 0, 0, minus 25. So it goes on top of the object and then goes down by 25, catches the object, moves to the queue, opens eye, goes back to sub palette. Okay, so it comes back for the third object. Then it becomes 2 plus 1 is equal to 3 now. Okay, then it becomes 3 plus 1 is equal to 4, does the same loop. Then it becomes 4 plus 1 is equal to 5. Now it has exceeded. So if column is greater than max column, then 20. So it has come here now. So set row is equal to row plus 1. So row was 1, so it has become 1 plus 1 is equal to 2 now. Okay, and if row is greater than max row, then 30. Okay, so it is here, it is going to return. Okay, so if row is greater than max row, so what is the max row? Max row is 3. So if it has come here now, that means the columns have been exceeded, rows have been exceeded. So now it should exit the program. Okay, so basically what it is doing is it is setting the row to row plus 1. Now it is 2. Then if row is greater than max row, then 30. That means it will go return and it will exit. So it will return and then it will exit. Okay, now if it is not, then it will shift pick by minus 150, minus 30, 0. What is minus 150? So from here it is shifting by minus 150, which means minus 150 is 50, 50, 50. So it is here now, and it has gone to the second row, so it is here. Okay, so it is shifting minus 150, minus 30, so it's coming down and 0. Okay, so in the last class I talked about the method. From here you can go here, or from here you can also go here. Okay, so there are different ways of indexing. The way it is done here is this way, and then it shifts by this. Okay, set column is equal to 1. So the first column it goes back, and then it returns to 30. Okay, 30 is returned. So what it has done is, after the rows are, after the last column is over, it goes to the top of this one, resets the column to 1, and then starts picking again. Now the moment it comes here and it has exceeded the rows and columns, then it will exit, then it will end the program and exit. Okay, so this is an example of a Puma robot program written in VAL language, and the logic is very, very simple. Okay, the logic is extremely simple, that you can actually write this program by yourself. But of course, this is for a single robot. If there is more than one robot or more complex tasks, then you know that it can become more and more complex. There was, of course, no communication in this case. So you have to add some communication if SIG has to be added. If the robot is, for example, it is a conveyor now. Now the part is coming on the conveyor is rotating. And if the part comes, there is a sensor which picks up the sensor information. Okay, and then it takes corrective action, and then it informs the robot. So in that case, you can put it on channel number 1. Okay, if channel 1 is on, then do something, then move, or then go to line number 10. Okay, so some logic has to be done here. So some kind of logical statement can be there with using the signal command. Okay, so the robot normally would require some kind of communication command. So this gives a very simple example of how to write a program. Now you can see that writing a program is actually not very difficult for simple applications like simply pick and place. Now, if you're writing a program which is for more complex operations like pick and place from a conveyor, index it, the same indexing we just studied can be done here also. Okay, exactly the same way it can proceed. But this will require some kind of signal condition. This will require some kind of signal lines between the robot and the conveyor. So it can be 1 and 2. Okay. Now for more complex parts or complex tasks like in a flexible manufacturing system, there can be different kind of sensors which are coming into the robot. Okay. There can be different machines which the robot is interacting with. So this kind of a program becomes complicated. Okay. It's not impossible, but it's very difficult to write because you have to worry about cycle times. Okay. There is a chance of a deadlock in a program going on. So everything has to be optimized, and this actually shows the difficulty in robot programming, that the robot program has to be optimal, and after it is optimal in terms of time, it has to ensure safety, and it has to guarantee that with all the errors that are there in terms of resolution, accuracy, repeatability, there is going to be no damage anywhere. And that is something which is very expensive for application of robots. So basically what we see here is that robot programming, the basic programming is pretty simple, but then for complex industrial applications, you will need the help of professional companies which do this, and that is what adds to the cost of the robot. Okay, so we will stop this class today, and this is also the last class. So I hope that you enjoyed the course, Introduction to Robotics course. Okay, and we hope that you have learned about the basic fundamentals of robotics, and with whatever I have discussed, you can now move on to more advanced courses like advanced robotics, okay, robot motion planning for mobile robots and for arm robots, because the kinematics and the dynamics that we have done remains the same. So I wish you all the best, and I hope that you'll be taking more advanced courses in robotics in future, and wishing you all the best. Thank you.